Now we start our morning session, and Alexei will.
Yes, the first speaker of today's morning session is Dmitry Tимашёв from Moscow State University. He will tell us about component group of a real algebraic group. Please.
Thank you for the introduction. It's my great pleasure to be here at the conference dedicated to the anniversary of Viktor Matveevich. And it seems that the sound is going on. Yeah? Is it okay with the sound? I'm sorry. Yeah, I see. So first of all, I would like to wish to Viktor Matveevich many fruitful years. Let me say that my talk will be about algebraic groups and Lie groups. Most of you here are topologists and geometers, but I know that Lie groups are also in the broad scope of interests of Viktor Matveevich, so this somehow justifies my choice of the subject of this talk. So I will speak about algebraic groups defined over real numbers. Such a group I will denote by G. What is it? Naively, you may think about an algebraic group over real numbers as a quasi-projective variety embedded in some projective space and given in this projective space defined by polynomial equations and or inequalities given by polynomials with real coefficients. And also, since it is a group, the group law should be also given by polynomial formulae in projective coordinates with real coefficients. So given this, you may consider the set of complex points of these algebraic groups, which is just the set of solutions of the system, of this defining system of equations and inequalities with complex coordinates. And it is a complex Lie group in the usual sense. And you also may consider the set of real solutions, the set of real points of this algebraic group, and it is a real Lie group. We also have the complex conjugation map on the complex locus of my algebraic group G, which just sends a point to another point in this group, whose projective coordinates are just complex conjugates. So this complex conjugation is given just by conjugation of complex conjugation of all coordinates. And of course, we have a simple criterion. So an element G belongs to the real locus of big G if and only if it is fixed by the complex conjugation. So this is somehow very clear and naive viewpoint on algebraic groups defined over real numbers. But you may also think about this concept more conceptually in a coordinate-free way. So you may define a real algebraic group as a complex algebraic group, that is a complex algebraic variety with the group structure, with the group law, equipped with a real structure. What is a real structure? This real structure is an involutive group automorphism, which is anti-regular. Anti-regular means that it sends regular functions to complex conjugates of regular functions. So it sends the structure sheaf to its complex conjugate. You may say that anti-regular is an algebraic counterpart to anti-holomorphic. So given such an anti-regular group involution on a complex algebraic group, we can say that it gives you a real structure and it defines you a real algebraic group, an algebraic group over real numbers. So in fact, these two definitions are equivalent. So the first one is naive, coordinate dependent, and the second one is coordinate free and more conceptual. For me, the second definition will be the working one in my talk. So I will use this involution sigma through all my talk. Okay, so assume now that my algebraic group G is connected in Zariski topology. So let me recall you that Zariski topology is the usual topology used on algebraic varieties over an arbitrary field. In this topology, closed subsets are just algebraic subvarieties, closed algebraic subvarieties. if G is connected in Zariski topology, then its complex locus is a connected Lie group, a connected complex Lie group in the usual Hausdorff topology on Lie groups. But the real locus may be disconnected, maybe a disconnected real Lie group. Maybe one of the most obvious examples which come to your mind at first is the general linear group. GLN of C is connected, while GLN of R has two connected components distinguished by the sign of the determinant. So this phenomenon makes the following problem natural and interesting. Let's consider the set of all connected components of this real locus G of R. Among them, there is the identity component, the component containing the unit element, the identity element. It is a normal Lie subgroup, open and closed Lie subgroup in G of R. And it is well known that all other components are just cosets of this subgroup in the big group, in the whole group. So the set of connected components of the real locus of G comes equipped with a group structure, just the quotient group of G of R modulo the identity component. And it is a natural question to compute this group. Actually, to my best knowledge, not much was known before. Of course, this problem was addressed already by classics in Lie groups. Among known results, I would like to mention first a theorem going back to Elie Cartan, saying that if G is semi-simple and simply connected, then the real locus of G is also connected. So the component group is trivial in this case. And yet another theorem of how many? 60 years old, yeah, almost 60 years old, is due to Matsumoto. It concerns linear algebraic groups. So a linear algebraic group is just a subgroup in some GLN. The theorem of Matsumoto says that if G is linear, yeah?
Plus minus degree n. How many elements?
Well, 2 to the n, of course. This is a cyclic group of order 2 to the power n, 2 to the n. So this theorem says that actually for any linear algebraic group defined over real numbers, the component group of the real locus is just an elementary, a finite elementary abelian 2 group. So it is a product of several copies of the cyclic group of order 2. Of course, this component group was computed in many examples. But as for general results, to my best knowledge, this was all known before recently. So what I'm going to do in my talk, I'm going to present you a complete solution to this problem, the computation of component group for any algebraic group, any connected algebraic group defined over real numbers, not necessarily linear. This is important. So for abelian varieties, it works as well, for instance. The complexification. So it is a simply connected algebraic group. So the complex locus is a simply connected complex algebraic complex Lie group. You may say like this. Yes, but the real locus may be not simply connected, of course. It may have a non-trivial fundamental group. Okay, so to proceed, I need to recall some basic theorems, basic structure theorems in algebraic groups. They basically go back to Rosenlicht and Chevalier, but for me, a good reference is a survey paper by Michel Brion. This is this paper, the first one in the list of references. And I will refer to this paper for the results which I quote about the structure of algebraic groups. So the first thing I need is the Rosenlicht decomposition. any connected algebraic group can be decomposed into a product, not a direct product, just a product of two subgroups. The first one, GF, is the largest connected affine algebraic subgroup. Affine means it is an affine algebraic variety, or this is the same as linear algebraic subgroup. So GF is a closed subgroup in some GLN, and it is known that any connected algebraic group contains the biggest one, the biggest linear algebraic subgroup. Not just maximal, but the biggest. It contains all other linear algebraic subgroups in G. And of course, since it is unique, being the biggest one, it is unique. Since it is unique, it is normal. The other factor, G and, is the largest, again, the largest one among connected anti-affine subgroups. What is anti-affine? This means that there are no non-constant regular functions on this algebraic variety G and. For instance, any abelian variety is a good example. Any abelian variety is an anti-affine algebraic group, but not only. There are other anti-affine algebraic groups which are not projective varieties, but still they have no regular functions. And this anti-affine factor is not just normal, it is central. It is commutative and it commutes with the whole group G. It is a central subgroup. What is the structure of these two factors? Well, as for the affine factor, it is well known. It is a linear algebraic group, a connected linear algebraic group, and it has the Levy decomposition into the semi-direct product of the unipotent radical. G uni is the unipotent radical. It is the largest normal unipotent subgroup. Unipotent means that it can be embedded in a group of upper uni-triangular matrices of some size. And the second factor is reductive. It is called Levy subgroup, a Levy subgroup. It is not unique, but it is unique up to conjugation. So it is essentially unique. This reductive part in turn decomposes into an almost direct product of the semi-simple part, which is just the derived subgroup. GSS is the derived subgroup of G red. And it is semi-simple, connected and semi-simple. And the second factor, S, is the connected center. It is an algebraic torus. So an algebraic torus is just a product of several copies of the multiplicative group of the field. What is an almost direct product? Maybe it is not quite a common name. It is almost the same as the direct product. The difference is that you allow finite intersection of factors. So both factors are normal, commute, but you allow finite intersection of them. This is the structure of the linear, of the affine part of G. And now what about the anti-affine part? It has the following structure. So you have this short exact sequence of groups, of algebraic groups, where the subgroup is just the intersection. The subgroup is just the intersection of the anti-affine and affine part of G up to connected components. So it is the affine part of the anti-affine part of G. This is in the kernel of this middle arrow of this map. And the quotient group is an abelian variety. So basically any anti-affine algebraic group is an extension of an abelian variety by a commutative connected algebraic group, this one. The structure of this commutative connected algebraic, of this commutative connected linear algebraic group, G and F, is very simple. It is also well known what are connected linear algebraic groups which are commutative. It is a product of two factors. The first one is an algebraic torus contained in S because it is central. And the second one is a commutative unipotent group. It is just the additive group of some vector space. I call it a vector group. And this group V is contained in the unipotent factor of the Levy decomposition. So this is the structure of anti-affine algebraic groups. And from this discussion, you immediately see that if you denote by Z the product of S of this central torus S with the anti-affine factor G and, this is an abelian algebraic group, connected abelian algebraic group, and the whole group G decomposes into a product of the unipotent radical of GF and this group G semi-simple, almost direct product with Z. It is just the collection of the outcome of the collection of decompositions above, which you see above. So we use this last decomposition in our study of connected component of the real locus of G. And the first remark, it is an easy lemma, is that actually this last decomposition, which you see on the last line, extends over the real loci. So the lemma says that for the real locus of G, yes, yeah.
Why do we need this anti-affine part? Can we generate our G by affine part and this abelian variety A?
Well, A is not a subgroup in G. A is a quotient group of this entire affine part. You cannot split this short exact simplics in general.
You cannot find in G such a subgroup A.
Not necessarily. Okay. So the lemma says that the last decomposition carries over the real locus. Actually, well, I even seem to have. So how much time do I have? 50 minutes. Yeah, 50 minutes. So I think that it seems that I'm going quite quick. So I seem to have even time to give you a proof of this lemma, because it is at least one or a couple of proofs should be given in the talk. And this one is very simple. So I just give you the proof in order to show that these things are quite accessible. So if you have a real element in G, it can be decomposed into a product of elements in the two factors, G uni and the second group. But these two elements, these two factors are not necessarily real. So U and H are not necessarily real. But G is real, and it coincides with its complex conjugate. So we have this equality. From this equality, you immediately see by dividing with U and H on the other side and H bar on the other side, you see the second equality. So on the left, you have an element in G uni, and on the right, you have an element in the second group, GSS cross Z. This means that both sides belong to the intersection of these two groups. And this intersection is exactly this vector group V. So we denote this one and the same element by small v. And this element is, as you immediately see from this equality, this element V is conjugate to its inverse. By the way, we shall see this condition in the sequel of my talk. Now, the vector group has a nice property. You can extract a square root of each element in V. So taking the square root of V and shifting both sides, both factors in this first decomposition by this element. So you replace U with U times V 1/2. And you replace H with H times V minus 1/2 on the left. So you see again that these two elements belong to G uni and GSS cross dot Z. But now it is easy to check from the above equality that these factors are already real points. They are fixed by the complex conjugation. So starting from an arbitrary decomposition of G, of the real point G, we obtain another one whose factors are also real. And this proves this decomposition of real loci. Okay, Now, coming back to our question about connected components, there is the exponential map yields an isomorphism of algebraic varieties between the Lie algebra of the unipotent group and the group itself. So just the usual exponential series is a polynomial in this case, and you have an inverse map, so the exponential map is an isomorphism. This means that the real locus of the unipotent group is identified with the real locus of its Lie algebra, which is just a vector space, so it is connected. As a corollary, we immediately obtain that the component group of the real locus of G is the same as the component group of this vector, GSS cross dot Z. So in order to compute the component group of the real locus, we can neglect this unipotent vector. We can forget about it. So we may and will assume for the sequel that my algebraic group G is a semi-direct product of a semi-simple group and the connected center. Okay? So no unipotent part, no G uni is present now in this decomposition. We reduced everything to algebraic groups of this kind. Semi-simple group and the connected center, the almost direct product of these two. Okay. So this is the first tool which I use in the proof, and yet another tool is Galois cohomology. I will need some basic things about Galois cohomology to prove the main result. So I will speak only about Galois cohomology over real numbers, which is much simpler than in general. But anyway, a classical standard reference book in Galois cohomology is this classical book of Serre, which actually appeared in 1968, but it was in French, and this is the first, maybe, or maybe not the first English translation of this book. Okay, so what is Galois cohomology over real numbers? First, we define the set of one cocycles. One cocycles are just complex points of G, which are conjugate to their inverses. So they satisfy this equation. Z bar equals to the unit. On the set of one cocycles, there is an action of the complex locus of G by twisted conjugation. So it differs from the usual group conjugation. You see, in the last factor, you replace G inverse with G bar inverse. So you twist by complex conjugation on the right. Clearly, or maybe it is easy to check that twisted conjugation preserves the set of one cocycles. And the one cohomology, the first Galois cohomology set, is just the set of orbits for this twisted conjugation action on the set of one cocycles. It is important to note that the first Galois cohomology set, or maybe the full name is the first Galois cohomology set of the absolute Galois group of real numbers with coefficients in G, but it is too long, so I will speak just about first Galois cohomology of G. So this cohomology set is just a pointed set, not a group in general, as you are used to. You are topologists, you always work with cohomology groups, but this is not a group in general. It is a pointed set. The base point is just the distinguished point in this set is just the class of the unity element. Of course, if G is abelian, then it is a group, a true group. But in general, it is a pointed set. Nevertheless, although Galois cohomology is just a set, we have some piece. We still have some piece of usual cohomological formalism. For instance, we have a long exact cohomology sequence associated with a short exact sequence of algebraic groups. This cohomology sequence is actually not that long, but still, I mean, 6 terms. And all maps in this sequence are more or less obvious, except maybe for this arrow in the middle, from the real locus of C, from the real locus of the quotient group, to the first Galois cohomology set of the subgroup A. This map is described as follows. So given a real point C small in C, you can lift it to B, but the lift, this small b, is no longer a real point. It is a complex point. So it may differ from its complex conjugate. But since the image in the quotient group is real, the difference belongs to A. So if you divide B bar by B, then this will be an element in A. And it is easy to see that this ratio of two group elements is a one cocycle. So you may take the cohomology class of this element, and you get in here, in the Galois cohomology set of A. This is this middle arrow. And it is easy to check that this sequence of maps of groups and pointed sets is exact. So what does it mean, exact? The same. So if you have a map of pointed sets, you define the kernel of this map as the set of all points which map to the distinguished point in another set. And exactness means that the kernel of one arrow coincides with the image of the previous arrow. So the same thing as in the group setting. This exact cohomology sequence is actually very instructive in usage of Galois cohomology in various questions about algebraic groups and their actions over non-algebraically closed fields. But for me, this is a tool to compute the component group. I will explain how later. Okay. Now let me turn. Let me approach to the proof of the main result. Let me recall some notation. So G is my connected algebraic group, which I suppose to be decomposed into a semi-direct product of a semi-simple group and a connected abelian group, Z, which is just the connected center of G. Let me denote by G as C. SC stands for simply connected. The simply connected cover of GSS. So any semi-simple algebraic group admits a finite cover which is simply connected. Both algebraic, yes. So all this can be done in algebraic settings, but simply connected means that its complex locus is a simply connected complex Lie group. You may say like this. And let me also denote by Z, by this small z, small Gothic Z, the Lie algebra of big Z. Now, I can construct the simply connected cover of G, or maybe better to say of the complex locus of G. I may construct the simply connected cover of G in the following way. So let me consider G tilde be the direct product of the simply connected cover of GSS and the Lie algebra of Z. I will equip this direct product with the structure of a Lie group or if you like, of an algebraic group in the obvious way. So the first factor is already an algebraic group, and the second factor is just a vector space. So the addition operation turns it into an additive algebraic group. This is what I called vector group. The vector group of this vector space Z. And this map from G tilde to G is defined on both factors. So on GSC, it is just the covering map over GSS. This is the, on GSC, it is just the universal cover of GSS. And on the second factor, on Z, it is just the exponential map. So Z is a connected abelian algebraic group, or a connected abelian Lie group. And the exponential map from its Lie algebra to the group gives you a universal cover, actually, of this Lie group. So this guy, G tilde, is indeed a universal cover of G. The kernel, gamma, is a discrete subgroup in G tilde. And actually, this gamma shows up already on the level of maximal tori. So I need some more notation. Let me denote by the letter T with various subscripts, maximal algebraic tori in the groups under consideration. So TSS is the maximal torus in the semi-simple part of G, and TSC as well is the maximal torus in its universal cover. Now there is a subsequence in the exact sequence above, which already consists of abelian Lie groups. So the first one is the product of this torus, semi-direct product of this torus and this abelian group Z. And the second one is a direct product of the maximal torus in G simply connected and this vector space Z. And the kernel of the above, the kernel in the above exact sequence already shows up in here. So if you want to understand the structure of this group gamma, of this discrete group gamma, you may consider the following commutative diagram.
But Z is also the product of a torus and a vector.
Z is also a torus. No. Z is more complicated because Z is, how to say, it involves also the anti-affine part of G. So its structure is more complicated. I would say, yeah, maybe I can show you again this. I can show you again this this exact sequence, and Z is somewhere in the middle in here. But also Z may involve some part of this torus S, which you can just add to here and to here, and so this exact sequence carries over to Z. Yes, and now since this middle arrow is a covering on the level of Lie algebras, we have an isomorphism. And on the other side, these vertical arrows are maps from the Lie algebras to the groups. These groups are abelian, so the maps is just the exponential maps for the respective Lie groups, which we normalize for convenience by taking this factor 2 pi. This is just for convenience of various formula. So various formula look better in this case. Again, the kernels of these vertical maps, exponential maps, are some lattices in the Lie algebras. Looking at the commutative diagram as a whole, you see that gamma is just the quotient of this lattice, lambda multiplied by I. I is the imaginary unit, square root of -1, which again is a multiplier added for convenience. So gamma is just the quotient group of this lattice modulo this lattice, and this lattice is just the co-root lattice of this semi-simple algebraic group GSS or GSC. They have the same set of roots and co-roots multiplied again by the imaginary unit. As a conclusion, we have this formula. So the group gamma, which is of course, let me switch to the previous slide, the group gamma, which is of course identified with the fundamental group of G, of the complex locus of G. This group gamma is isomorphic to the quotient of two lattices, lambda modulo Q check. So this is, in a sense, a very explicit description of the fundamental group of the complex locus of G. Of course, this description is well known, for instance, for semi-simple groups, in which case lambda is just the lattice of co-characters of the maximal torus. Now, having this in mind, let's consider the long exact Galois cohomology sequence associated with this short exact sequence of groups. So G mapped from G tilde with the kernel gamma. The long exact cohomology sequence, actually a piece of it, looks like this. So here we have the real locus of G tilde mapping to the real locus of G, which maps by the connecting map to the first Galois cohomology group. In this case, it is a group because gamma is commutative. To the first Galois cohomology group of gamma. Gamma is a lattice. This abelian group, maybe not lattice, this finitely generated abelian group. And the last arrow maps this first Galois cohomology set of gamma to the first Galois cohomology set of G tilde. What is the structure of groups and sets in this exact sequence? So first of all, we remark that for G tilde, its real locus decomposes as the product of real loci of its semi-simple part and of this vector part. Yeah. The vector group Z is unipotent, and this means that it is acyclic in the sense of Galois cohomology. So if you compute the Galois cohomology set of G tilde, then only the semi-simple factor survives. So you may forget about Z when computing the Galois cohomology of G tilde. As for the real locus, let's recall the theorem of Elie-Cartan that G as C being simply connected, this real locus is connected. And of course, the real locus of the second factor is connected, it's just a vector space. So you see that the real locus of G tilde is connected. And this means that it maps exactly on the connected, on the identity component of the real locus of G. So G tilde of R maps onto G of R naught. When you take the quotient by G of R naught, you immediately get the following exact sequence. So you have the component group on the left, the component group which we seek, which we look for. You have the component group on the left mapped to the first Galois cohomology set of gamma, which in turn is mapped to the first Galois cohomology set of this simply connected semi-simple group. And actually, this map is quite explicit. So here you see the formula for this map. We see that in order to compute the component group, it remains just to compute the kernel of the Galois cohomology map, of this Galois cohomology map. So everything is reduced to computation of the kernel of this map. And now I can formulate the main result. Well, maybe before formulation of main result, I need some more piece of some piece of notation, some extra piece of notation. So you have this lattice gamma on which the involution sigma given by the real structure acts, because it acts on everything related to G. This is an involutive linear operator on the vector space spanned by gamma. And you can decompose this vector space into eigenspaces with eigenvalues 1 and -1. So this is this decomposition. And let me denote by lambda plus or minus the intersection of lambda, of this lattice lambda, with these eigenspaces. We also have bigger lattices, slightly bigger lattices, lambda plus or minus tilde, which are the images of the projections of lambda onto these eigenspaces. This lambda plus minus tilde contains lambda plus minus, obviously, and also is contained in lambda plus minus compressed twice, just because sigma is an involution. It's switched in between. Yeah, okay. So also let me recall decomposition of the maximal torus, actually of any algebraic torus defined over real numbers, into factors of two types. So there is a unique decomposition of any algebraic torus. I will use it for the maximal torus in the semi-simple part of G, into a product of two subtori. One of them is split. Split means that the real structure on this torus is given just by conjugation of complex coordinates. So the real locus of the split torus is just a product of punctured line, several copies. And the second factor is anisotropic. Anisotropic means that the complex conjugation is given by replacing coordinates with conjugate inverses. For an anisotropic torus, the real locus is compact. It is a compact torus in the usual sense, in the topological sense. It is a product of a circle, of a unit circle on the complex plane several times, several copies. Actually, split tori play a big role in studying the structure of semi-simple or reductive algebraic groups. And there are several possible choices of split tori, which are useful for those or. Okay, one of the approaches is so-called Satake approach, in which we choose the maximal torus in the semi-simple group in such a way that its split part is a maximal split torus in this group. And we shall adopt this choice. And taking this choice, now I can formulate the main result. So this is a formula for the component group of the real locus of my algebraic group G. So the component group is isomorphic to the quotient of two lattices. So the first one is this plus part, sigma fixed part of the lattice lambda. And the second lattice is the sum of two sublattices in here. So you take this lambda plus tilde, which is just a projection of lambda onto the eigenspace fixed by sigma, and multiply it by 2. So you take a twice bigger lattice, in a sense. Maybe not twice bigger. You multiply all vectors by 2. And the second one is the part of the co-root lattice belonging to the fixed point space of sigma. So these lattices are very explicit. If you are given your algebraic group, you can take this lattice, compute them, and compute the quotient. So this is a very explicit description of the component group. And in particular, it gives you representatives of connected components. So you may pick up elements in pick up a single point in each connected component. So this is a very explicit description. So this is the same theorem. I just moved it to the next slide. Maybe I will, before showing you some example, maybe I will say a few words about consequences of this theorem. So the first corollary is immediate from this formula. It is an extension of the result of Matsumoto. We see that the component group is an elementary abelian 2 group for any algebraic group, not necessarily linear, as was in Matsumoto's work. And also in the case of reductive groups, the picture looks simpler. So this lattice lambda is just the co-character lattice of the maximal torus in my reductive group G. And lambda plus is the co-character lattice of the split part of this maximal torus. Now observe that here this TS denotes the split part of the maximal torus in G, not just in its semi-simple part. And you immediately see from the formula given in the theorem on the second line a corollary, which is also due to Matsumoto in the reductive case, that actually each connected component of the real locus of the reductive group G intersects the set of order 2 elements in the maximal split torus. This is actually how Matsumoto deduced that the component group is an elementary abelian group, but he didn't know its precise size. The precise structure of this group is given, for instance, by this formula. So we recover previous results of Matsumoto and get something more. I have a few minutes and I prepared actually 2 examples to illustrate the main theorem. Maybe I'll skip the first one because it is about linear algebraic groups. You have to introduce monotation. Instead, I turn to the second example about elliptic curves. So elliptic curve, an elliptic curve is just an abelian variety of dimension 1. So it is a quotient of the complex plane modulo a lattice of rank 2. So you observe this factor I. It is just for convenience in order to get some formulae looking better. The connected cover, the universal cover, the simply connected cover of G is just the complex plane. It can be identified with the Lie algebra of G. And the covering map is the exponential map, which I denoted previously by this E, fancy E. It is just the quotient map modulo this lattice. In this case, coming back to the general formula, you see that there are no coroots, no roots, no coroots. The coroot lattice is empty. And the formula for the component group looks in this very simple way. So you have to take the sigma fixed part of lambda, lambda plus, and divide it by lambda plus tilde multiplied by 2, by twice lambda plus tilde. Actually, this formula works not just for elliptic curves. It works for any abelian variety of any dimension. So the same formula, looking in the same way, holds for the component group of the real locus of any abelian variety. But let me, for simplicity, restrict to elliptic curves. If you rescale, you may assume that the period lattice, this lattice I lambda, is just z plus z omega. So the fundamental periods are the unit and some complex number omega, whose real part is in between -1/2 and 1/2, with 1/2 excluded. Let me show you in this picture. So since we assume that this elliptic curve is defined over real numbers, so this lattice lambda, the period lattice lambda, should be fixed by the complex conjugation. And this means that we are actually left with two possibilities. So the first one is when the second fundamental period is pure imaginary. And the second one is when its real part is -1/2. Only two possibilities are left with these restrictions. Now, in the first case, if omega is pure imaginary, then you immediately see that lambda plus and lambda plus tilde are the same. And this sigma fixed part of the period lattice is just spanned by the second fundamental period, by this omega lying on the imaginary line. So that looking at this formula above, we see that the group of components is just the cyclic group of order 2. In the second case, the situation is different. In this case, lambda plus tilde is twice bigger than lambda plus. And actually, this quotient group is trivial. So the real locus of the elliptic curve is connected in this case. And actually, my final slide, maybe last but final slide, says that this can be seen, of course, very explicitly in a different way. So if you write your elliptic curve in the Weierstrass normal form, with these coefficients P and Q given by well-known Eisenstein series, then you can compute the discriminant of this cubic polynomial f defining your elliptic curve. And actually, in the first case, you see, by the way, since there are many students, one of previous lectures, I guess, that Ivan Babenko suggested to give exercises. So this is a good exercise for students to prove that in this case, the discriminant is positive. So this means that the cubic polynomial, the graph of this cubic polynomial looks like this. And if you extract square roots, you see that the real locus of your elliptic curve looks like this. So you have two connected components are visible. In the second case, you again immediately, well, maybe not immediately, you can compute the discriminant and prove that it is negative. And this means that the graph of the polynomial f looks something like this. And when you take square roots, you get this picture for an elliptic curve. So you see that the real locus is connected. Actually, these two pictures, you can see pictures of this kind in any textbook on elliptic curves. I'm pretty sure that everyone knows these pictures. Okay. So my final slide is about references. I can comment about them if you like, but let me stop here and thank you for your attention. And of course, yeah, I would like to wish many happy returns again to Viktor Matveevich. Thank you so much.
Thank you. Are there any questions or comments?
Could you say again why that component group is a two group actually? Because in the why this there is also this co-root lattice is involved, right?
You mean in general, yeah?
Yes, in general, yeah.
Well, actually, this co-root lattice is indeed involved, but it doesn't make the situation worse because you can even forget about this second summand. If you take the quotient of lambda plus modulo twice lambda plus tilde, then you already get a group Z2 to some power because of this conclusion.
Yes. And yeah, I actually have another one, maybe more general. So you mentioned holomorphic situation at the very beginning. So it seems that large parts of your arguments carry over to the holomorphic situation as well.
Exactly. So, actually, I use the algebraic setting only in exhibiting the structure of G and so on. Of course, and also when we speak about Galois cohomology, it can be replaced by group cohomology with coefficients in your non-commutative group G. So yes, you are absolutely right.
So that also holds for the holomorphic.
Most of arguments work in the holomorphic settings.
But you have this Levy decomposition and this.
Well, this I mean. You have to use some structure results on complex Lie groups with the real structure. Yeah. If you have structure results of this kind or something like this, then I'm pretty sure that everything extends.
Thank you.
Please, more questions and comments? If not, then we can thank the speaker again.
Thank you.
And now we have a coffee break.
Можно с тобой дошел?